Multiparadigm Data Science with the Wolfram Language. Section 4, Assembling a Multiparadigm Toolset. A review of tools available for assembling a multiparadigm project workflow cannot be complete without the most popular machine learning technique of the recent times, the neural network. And we have good news and bad news on this account. The good news is that the Wolfram Neural Net repository and the neural net framework in the Wolfram language makes it really easy to incorporate this powerful technology into our project workflow. The bad news is that we could never do justice to covering this topic in just 10 minutes. But we could look at the resources we have available to incorporate neural networks into our multi-paradigm project workflow. The Wolfram Neural Net repository, it provides access to tried and tested pre-trained models, and we can use them as is or modify them as required with what is known as net surgery. This is definitely the recommended way to get started with neural nets. However, if we need to build neural nets from scratch, we can do that as well using the symbolic architecture provided by the Wolfram Neural Net framework. The Wolfram Language Neural Net framework is built on MXNet. Apache MXNet is an open source deep learning software framework. It is portable, scalable, and allows for fast model training on multiple GPUs. It is supported by Amazon Web Services, Microsoft Azure, NVIDIA GPU Cloud, and it can be used either directly or via an interface like the Wolfram language, as well as other languages like C++, Python, etc. The usefulness of frameworks is in the common features they provide to allow us to build and customize neural nets easily. With frameworks, we can build networks as chains or acyclic graphs of layers. The layers process arrays of numbers, kind of like neural activities. Encoders convert input to numerical arrays, and decoders convert numeric results to desired outputs like class labels or images. The frameworks provide implementations of loss functions, backpropagation, stochastic gradient descent algorithms, and so on, and are highly optimized to run on specialized hardware like GPUs. Now, neural nets can be used to perform tasks like classification or regression. They can be used for image processing, audio analysis, language modeling, and lots of other different things. The Wolfram Neural Net repository is a public resource worth exploring for the neural net models and examples of their application. For example, this is the Wolfram Image Identify Net v1, which is the power behind the Wolfram language function image identify. It can identify the main object in an image, which is an image classification task. The pre-trained neural net model can be downloaded from the repo and used on new images. The vanilla CNN for facial landmark regression determines the locations of the eyes, nose, and mouth from a facial image. It outputs numbers representing the coordinates of these points on the image and can be used by other functions to highlight the points on the image. Neural nets are being increasingly used for various image processing applications. For example, to solve the problem of segmenting an image of a driving scenario into semantic component classes, as done by the dilated ResNet 105 neural net model. To use this model, we need an evaluation function to handle net reshaping and resampling of the input and output. Integers from the model's output can be mapped to labels for each segment in the image and thus be used to obtain a segmentation mask for the given image. The colorful image colorization model, as the name suggests, can be used to colorize a grayscale image. It recasts image colorization into a classification problem by dividing the AB color space into a number of bins and picking the final color for each pixel according to its probability distribution over the bins. The model takes a grayscale image as input and outputs the A and B channels in the lab color space. So it needs an evaluation function to merge the output with the luminance of the input. Here is the output of using this function to colorize a grayscale image. The add-in style is an image stylization model that can transfer the style of one image to another. Here is an example of the model at work. And here is the output of the Wolfram Language function imagery style, which, as we can guess, uses a neural net internally. Among other examples of models in the repository is Baidu researchers' Deep Speech 2 model, which converts speech to text, an end-to-end model which takes as input normalized sound spectrograms and produces as output a sequence of characters. For text input, there is the collection of GLOVE word vector models from the CS department at Stanford, which provide vector representations for words. Here's an example of using the GLOVE 300-dimensional word vector model as a feature extractor with the feature space plot function to visualize words in 2D feature space. Incidentally, this model is also used for word embeddings in the Wolfram Language function find textual answer, which itself is a neural net trained using the Wolfram neural net framework. It answers questions by quoting the most appropriate excerpts of a text that is presumed to contain the relevant information. The current consensus in the neural net community is that building your own net architecture is unnecessary for the majority of applications, and such attempts can even hurt performance. Rather, adapting a pre-trained net to your own problem is almost always a better approach in terms of performance. Now, we have access to carefully designed and trained models in the neural net repo. So instead of going through the difficult and laborious task of building good net architectures from individual layers, we can transfer knowledge from nets trained on different domains to our own problems, a great application of the multi-paradigm approach to data science. We start off by looking for a net close to the problem we need to solve. Then download the model, perform minimal amounts of surgery on the net to adapt it to the specific problem, and train it on our data. Say we have a problem of classifying old movie posters according to the genre of the film. First, let's find a net suitable to our problem. Let's try the Wolfram Image Identify Net V1. Now, the last two layers are really specialized for image identify, so we can remove these layers using net drop. It's really easy doing net surgery in the Wolfram language since the nets are symbolic expressions that can be manipulated using a large set of functions like net take, net drop, net append, net join, etc. So we can use net join to combine the part of the pre-trained net with a chain of two new layers and our specific decoder. We train this net on our training dataset, freezing all the weights except for those in the new classifier layer. Now we can try it on our test set to see how the classifier labels the 4 test posters. One of the most powerful applications of trained nets is to use the knowledge they have gained on one problem to improve the performance of learning algorithms on a different problem. This is known as transfer learning, and it can significantly improve performance when you are training on small datasets. Okay, now let's try to build a neural net using the building blocks provided by the framework. The LeNet was a pioneer neural net model that was released in 1998 to solve the task of image classification using convolutional neural nets. It used the MNIST database of handwritten digits, which contained 60,000 training and 10,000 test grayscale images of handwritten digits. The LeNet model was trained to identify the digit from the image. Here's the pre-trained model from the Wolfram Neural Net repository. We can construct a neural net similar to the LeNet model by putting together different layers. This network takes as input a 28 by 28 grayscale image of a handwritten digit and outputs an integer between 0 and 9, the class label for that image. Now, a neural network's performance really depends on the parameters of the network. During the training process, we need to fit all these parameters with the help of the training data. Initially, the network parameters are unknown and set to random values. In this state, the network will just return some random result. So we train the network from scratch. NetTrain takes care of many details automatically, such as selecting an appropriate loss function, attaching encoders and decoders, initializing the weights and biases, choosing the optimizer and the batch size, and running the backpropagation algorithm. So let's test the trained net. We can evaluate the performance of the trained network using net measurements. We can also export the trained model to save it in the Wolfram developed WLNet format and import it back, either the whole net or its elements, for use later. Let's take a more detailed look at the building blocks of a neural network. A layer is the simplest component of a network. Layers only act on numeric tensors. They are differentiable, differentiability being a key property that allows the efficient training of the nets. Layers can run on GPUs and CPUs, and they can do shape inference. Certain layers have learnable parameters, and this is what makes learning possible while training the net. The linear layer is the simplest learnable layer. It computes a linear combination of the input given some weights and bias, something that a function like this would do. Here is a linear layer with 3 input nodes and 2 output nodes, and we can initialize the parameters for this layer. Here we can compare the results of our own linear function using the weights and biases from the initialized linear layer. The Wolfram neural net framework provides a huge list of layers to incorporate into your neural net model. Containers. We usually need to combine multiple layers together to do something interesting. This is where containers become useful. Chains are the simplest containers, and net chain can be used to chain together 2 or more layers. This function is really the computation that the chain here accomplishes. Since net chain cannot really take more than one input, net graph is used to build more complex networks. To accomplish something that this function would compute, we need to create a net graph. All of the layers are differentiable, and so are the containers. Containers can be nested, just like normal layers. The models in the repository are almost all in some form of a container. Neural net layers require as input numeric tensors. So to train and use nets on images, audio, text, etc., we need to use a net encoder to translate the data to numeric tensors. This encoder produces a 1x12x12 tensor from an image. It can be used on an image directly or on a file. A large collection of encoders are available for different data types. The output of a neural net is also a numeric tensor, but for a task like classification, we would want class labels as output. The net decoder converts numbers to non-numeric outputs for the net. This decoder will interpret a vector of probabilities over classes as a class label. The probabilities themselves can also be obtained. So, in this whirlwind tour of neural networks, we learned about the Wolfram neural net framework and the features it offers. We looked at examples of pre-trained neural net models in the Wolfram neural net repository and how to use net surgery to customize and adapt the models for use in different tasks for transfer learning. We put together a simple neural net according to the LeNet model to recognize handwritten digits of images. We also looked at the various building blocks provided by the neural net framework to understand how they can be used to design, build, and customize neural net models.